This is Professor Kitch, and welcome to this webcast on Part 2 of Soil Classification using the Unified Soil Classification System. There's only one learning outcome for this lesson, which is to properly classify coarse-grained soils using the USCS. We will be following ASTM Standard D2487, which codifies the Unified Soil Classification System. Before we start the classification system, let's review the important characteristics of coarse-grained soils. The first is particle size, that is, the average particle size. This will tell us if the soil is a sand or a gravel. Next is the distribution of soil particles. This will tell us if the soil is very uniform in size or has a large distribution of different size particles. We'll use this to determine if the soil is well or poorly graded. The percent fines, that is, the percent of clay and silts in the otherwise coarse-grained soil, is important. If there are a lot of fines, we'll need to include that information in the classification of the soils. If there are very little fines, then they won't be in the classification. And if there's a modest amount of fines, we'll have to describe both the coarse and fine-grained parts of the soil in the classification. The type of fines will be important, that is, whether they are clays or silts. And finally, there are some important characteristics which are not part of the Unified Soil Classification System. One is particle shape. While it's not technically included in the USCS, we can add particle shape descriptions to our USCS classification. Finally, the relative density of a soil is important to its behavior. However, this is an in situ property of the soil in the field, and the USCS classification is based on measurements of disturbed soils. So we can't say anything about the relative density in this system. However, if we have information about the density from a field test, such as the standard penetration test, we can add that information to the official USCS classification. Let's start by looking at the grain size distribution of three different soils shown in this figure. In addition to the grain size curves for the soils, this figure shows the size of the number 200 sieve, which is the dividing line between fine-grained soils and coarse-grained soils, and the number 4 sieve, which is the dividing line between sands and gravels. A quick look at this figure will show that all three soils are coarse-grained. That is, well more than 50% of each soil is larger than the openings in the number 200 sieve. Looking at soil A, we see that this is a soil with a very limited range of particle sizes. We can see that over 70% of the particles are between 0.2 and 0.4 millimeters in diameter. So the particles of this soil are very uniform. We call a soil like this poorly graded because the gradation of particles covers only a small range of sizes. In contrast, the size of particles in soil B covers a much wider range. We can see that over 80% of the soil is spread across the entire range of sand particles from less than 1/10 of a millimeter to 5 millimeters in diameter. We call a soil like this well graded because its soil particles are spread over a large range of sizes in a relatively uniform fashion. Soil C has an interesting grain size distribution. It covers a wide range of particles from less than 1/10 of a millimeter in diameter to over 30 millimeters in diameter. That is, from fine sand to coarse gravel. However, the distribution isn't uniform across this range. Close observation shows that over 40% of this sample is in the range from 20 to 40 millimeters in diameter. Another 40% is in the range of fine to medium sands, 1/10 to 1/2 a millimeter in diameter. Only a small portion of the particles in this soil are in the coarse sand to fine gravel range. We call a soil like this gap graded because it consists largely of two different size ranges with a gap between them. This is a special case of a poorly graded soil. In this case, The particle size covers a large range, but it isn't well distributed across that range. To be able to quantify the gradation of a soil, ASTM Standard D2487 uses two measures of gradation. The first is the coefficient of uniformity, C sub u, which is defined as D60 over D10, where D60 is the diameter for which 60% of the soil particles are finer, and D10 is the diameter for which 10% of the particles are finer. For example, looking at soil B, D60 is 1 millimeter, and D10 is 0.12 millimeters. The coefficient of uniformity is a measure of the slope of the grain size distribution curve between 10% passing and 60% passing. Soil A has a very steep slope in this region. Soil B has a shallower slope, and soil C has a yet more shallow slope. C sub C is actually proportional to the inverse of the slope of the curve, so soil C has the largest coefficient of uniformity, and soil A the smallest. For a soil to be well graded, we want it to have a relatively shallow slope like soil B, rather than a steeper slope like soil A. ASTM Standard D2487 specifies minimum values required for a soil to be classified as well graded. For sands, C sub u must be greater than 6. For gravels, it must be greater than 4. If we use only the coefficient of uniformity to define being well graded, soil C would be well graded too. However, it's gap graded rather than well graded. To identify gap graded soils, we use a second measure called the coefficient of concavity, C sub C, which is defined as D30 squared divided by the quantity D10 times D60. This measures whether the grain size curve is concave up between D10 and D60 as seen in soil B, or concave down as seen in soil C. ASTM Standard D2487 requires well-graded soils to have a coefficient of concavity between 1 and 3. Gap-graded soils like soil C will have a C sub C outside this range. So, for a soil to be well graded, it must have a coefficient of uniformity greater than 6 for a sand or greater than 4 for a gravel, and a coefficient of concavity must be between 1 and 3. Before moving on, I'd like to contrast geotechnical engineering terms with geology terms as they relate to gradation. Geologists use the terms well sorted and poorly sorted when discussing grain size distribution of soils. This language is just the opposite of that used by geotechnical engineers. To a geotechnical engineer, a well-sorted soil will be poorly graded, and a poorly sorted soil will be well graded. So be careful when you're talking to a geologist about soils. It's easy to be misunderstood. It's not that one of these descriptions is right and the other is wrong. It's just that geologists are talking about the process that formed the soils, while engineers are talking about the quality of the soil itself. To understand how coarse soils are classified in the USCS system, it's helpful to think of these soils as being grouped into 3 categories. The first category is what we can call clean sands and gravels. These are soils with very little fine material. Essentially, they're all sand and or gravel. We classify these soils based solely on their particle size and gradation. These soils will be classified either as SW, well-graded sand, SP, poorly graded sand, GW, well-graded gravel, or GP, poorly graded gravel. The second category are those sands and gravels with a lot of fine material. In this case, the behavior of the soils will be largely governed by the size of the coarse material and the type of fine material. So these soils will be classified as SM, silty sand, SC, clayey sand, GM, silty gravel, and GC, clayey gravel. The third category are soils with a moderate amount of fine material. These are in-between soils and will be classified both on their gradation and on the type of fine material they contain. These soils will get a dual classification such as SWSC, well-graded sand with clay, or GPGM, poorly graded gravel with silt. These three categories aren't an official part of the ASTM standard, but they help us to understand the classification process. With these three categories in mind, let's take a detailed look at the coarse grain soil classification process. We will use this flowchart to classify coarse grain soils. This is figure 5.7 in your text, or figure 3 from ASTM Standard D2487. Remember, to start using this flowchart, we must have already determined that the soil is either a sand or a gravel. That is, more than 50% of the soil must be retained on the number 200 sieve or larger. Once that's determined, the first question we need to ask is there more gravel or more sand? If there's more gravel than sand, then we'll be using the top half of the chart. If there's more sand than gravel, we'll be using the bottom half of the chart. The second question we'll ask is how much fine material is there in the soil? If less than 5% passes the number 200 sieve, then it's a category 1 soil with very little fines, a clean sand or gravel. If more than 12% passes the number 200 sieve, then it's a category 2 soil with a lot of fines. Otherwise, it's a category 3 soil with a moderate amount of fines. The third step is to determine if the soil is poorly or well graded. This applies only to soils with less than 12% fines. The fourth step is to determine the classification of the fine grained portion of the soil. This applies only to soils with more than 5% fines. Once we've completed this step, we can determine the soil's group symbol. The final step is to look at the percent sand if the soil is a gravel, or the percent gravel if the soil is a sand. This will allow us to give the soil its complete and official group name. If you think about breaking the chart down into these 5 steps, it's really not that complicated. So let's summarize the steps in classifying coarse grain soils. First, we ask, is the soil mostly sand or mostly gravel? Next, we look at the amount of fine material and determine if there's just a little, less than 5%, is there a lot, more than 12%, or is it in between? The third step is just for soils with less than 12% fines. Here we're asking if the soil is well graded. For sands, the coefficient of uniformity must be greater than 6. For gravels, it must be greater than 4. And for both, the coefficient of concavity must be between 1 and 3. In the fourth step, we'll look at the fine material for soils with more than 5% fines to determine if it's clay or if it's silt. And in the final step, we'll ask if there's more than 15% sand in a gravel or more than 50% gravel in a sand. Once we've completed all 5 steps, we can complete the classification and give the soil both its 2-letter group symbol and its full group name. Well, this gives you an overview of the process of classifying coarse grain soils in the USCS system. However, it's not really possible to understand the process without actually classifying some soils. In the next webcast, I'll go through a number of example classifications of coarse grain soils.